That's looking YouTube channel, and we are going to look at point load. Now, um the induced vertical stress is due to surface loading, right? And which is also known as the stress increase. Now, we looked at the various methods that we use to determine the stress increase at a particular depth. We talked about um simplified the simplified 2:1 method. Then we also looked at the elastic method. And we said that for the purpose of our course that we are going to do, we are going to focus on the elastic method. And we said the elastic method, we have two major methods under it, the Bosnick's Bosnick's method and the Westergaard Westergaard method. So these are the two methods, but our focus is going to be much concentrated at the Bosnick. And so the Bosnick, we are going to first of all look at the point load. Now the point load, we are considering the load that, for instance, we are considering the load that, let's say, light pole exerts on the ground. So we are taking that load, or the load that column of a structure would exert on a particular foundation. Do you get it? And so that is what we are considering as our point load. Now, for this point load, if so, for example, if I have a point load, let's say, if I have a point load in this direction, that is a point load. Now, the point load, if a stress is acting, this is my point load. Now, let me give the direction in this direction, then in that direction, then in this direction. Now, vertically or directly beneath the point load, I have my depth, right? Now, away from the point load, laterally away from the point load is what we call the radar distance. The radar distance laterally away from the point load is the what? The radar what distance, right? Now, if we apply a point load here at this particular point, so let me clean and give you the 2D dimension. So if this is our point load acting at this particular point, let me change the color. It is going to have influence directly below it and at a lateral distance. So, for example, if I apply point load here at a particular distance, let's say here, C. So, first, the C is going to have a depth, a vertical depth, and a lateral distance. So, from here to here is my lateral distance. Then from here to here is my what? Is my depth. Now, at this particular point, and at this particular point. So directly beneath the point load, the radial distance is 0. But at this particular point, the radial distance is what? R, right? Now, the stress that will be induced in the soil, this point, let me call here A, is going to be greater than the stress that is going to act at this point C. Because at this point C, there's a certain radial distance. So the influence of it is going to be a little bit small. Right? But if it is directly beneath it, it's going so when the load is going to have a directly vertical influence on it, and a lateral influence also on it. You get it? So if you remember, 2:1 that we give. If you apply the stress, right? If you apply the stress, it's going to cause a form of deformation in the vertical and in the what? In the lateral. So if you look at this figure here, if you look at this figure here, the stress was applied, the point load was applied here, right? Now directly beneath it, the radial distance is 0. Are you okay? Now we want the stress increase at this point. That is at a radial distance of what? R from where the stress was applied. So the radial distance from here to here. Do you get it? Are you okay? So we want the stress at this particular point. If we trace the stress at this particular point, the stress increase here is going to be, let's say, 1. And here, the stress increase here is going to be 2. At this particular point, the stress increase there is going to be greater than the stress increase at a radar distance, that is at a point that is not directly beneath it. A typical example is I have butter, then I compress the butter. Now you realize that the butter is going to shrink in size, but as it's shrinking in size, it's going to spew in its what lateral direction. Do you get it? It's going to spew. So, in as much as the stress is applied at this particular point, that is going to cause you to reduce that. It's also going to have a lateral effect on what? On the soil. And so there is relation we use, the relation that we use is what you can see. The relation that we use is what we can see. So the stress increase at a particular depth. So the stress increase at a particular point is equal to 3 times the force, right, over 2 pi, the depth that we are looking for squared, multiplying 1 plus the radial distance over the depth at which we are looking for the stress squared. And this whole thing to the power of 5 on what? On 2. So this is when you are given all the parameters. Then we also have the graphical method where we find the IQ, the influence factor. Now, the influence factor is gotten from a chart where we find R over Z. So you find R over Z, then you use the chart to find your IQ. So if you are using the chart, then you need that the stress increase is going to be the force that is applied over the depth squared, multiplying the influence factor. Now, if you look at the graphical representation, we've realized that the point load, this is the point load. When it is applied, as we are moving down, the stress decreases. That is directly beneath it. Then laterally, the stress also decreases. The stress decreases laterally. The stress decreases. So this is at a particular depth, at a constant depth. You realize that. So there are two things that are happening here. There are two things that are happening here. Let me erase this side and give you a better representation. So this is the depth, the direct depth, right? And this is the lateral um, distance. Now, when the point load is applied, when the point load is applied, it's at this particular point, right? The stress over there is the biggest. As we go down with it, the stress decreases. So this is in consideration of directly beneath it, right? Now laterally, the stress direct the stress increases when it is directly below it. But as you move away from the line of action of the stress, it decreases. Do you get it? So in actual sense, what we are saying that for point load, we always know that for stress increase, it decreases with depth. It decreases with depth. That has been established. Then for point load, for the case of point load, it also decreases with depth. Do you get it? And also decreases laterally. So at the same depth, for instance, at this particular depth, right? At this particular, yes, at this particular depth, directly beneath it, the stress is, let's say, 18. Then as you move away from it, the stress decreases and it comes to, let's say, 6. You get it? So directly beneath it, moving towards the lateral direction, it will decreases. then directly beneath it, in terms of depth, it also what decreases. So let's take note of these things. Have you seen that? And so I've also explained the equation. Now, when I was talking about the influence factor using the formula, so we are going to use this formula if all established parameters are given. Now, we are also going to use this formula if you are going to use the chart, the influence factor chart. So the influence factor chart is gotten from the influence factor chart. You first of all need to compute R over Z. That is the radial distance and the depth. Now, if the question specified that is directly beneath it, then the radial distance is zero. So in that case, this is zero. Now R over Z is zero. This is your corresponding influence or factor. So you compute your R over Z and you trace it to get your corresponding influence or factor. Now when you get it, you just find Q over Z squared. Whatever you get, you multiply it by what? The influence or factor. So we are going to take some examples and we are going to try our house on them. So see you in the next video. Bye.